So this leads us to our theorem for inverse. So the inverse function rule says that if I've got two functions that are inverses of each other, then the derivative of one is the reciprocal of the other, right? So if they're inverses of each other, then the derivative of f is 1 over the derivative of g, or in Leibniz notation is dy dx, is equal to 1 over dx dy, or if you like using reciprocal notation, this is dx dy to the minus 1. So the proof of this theorem is pretty straightforward. It starts with maybe a clever beginning. But if I look at dy dx times dx dy, now observant student will look at this and think, well, can't I just cancel out that and that's equal to 1? And in fact, since these are differentials, you actually can. But let's be formal about it to show that it's a valid move. It all comes from the standard part. So remember, dy dx is the standard part of the change in y over the change in x. That's what dy dx is. And dx dy is the standard part of the change in x over the change in y. Now, because standard part distributes across multiplication, I could also factor it out, rewriting this as the standard part of change in y over change in x times the change in x over the change in y. And these are all infinitesimals, or at least hyperreal numbers, and so we can cancel because they're real numbers. And this product is 1, so the standard part of 1 is 1. So now dividing through by dx dy, I get the result that dy dx is equal to 1 over dx dy. Or again, if you like, dx dy raised to the minus 1. So this gives us the ability to take the derivative of any inverse. So let's look at the example y equals x squared, where x is positive. Then, as we talked before, its inverse, x is equal to y to the 1/2. Now, we actually don't have a way yet. We will here in a second, but right now, we don't have any rule if our exponent is a rational number. Remember, up till now, our power rule only works if this is an integer. So I can't directly compute dx dy. However, I can use my inverse rule because dx dy would be 1 over dy dx. So if I can compute dy dx, then we're good. I just need to figure out what this is. Now that's pretty easy because y is equal to x squared. So the derivative of x squared dx. Now I'm not going through all the moves using differential because I feel like this is a very easy one. We've got the exponent, it's going to come down, and this will degree by 1. So this is equal to 2x. That's what dx squared is with respect to x, or this is our, if you will, our dy dx. So that means dx dy is 1 over 2x. Now it'd be nice to have this in our form, but we know that x is equal to y to the 1/2, so this is 1 over 2 y to the 1/2, or this is 1/2 y to the negative 1/2. Notice what happened here, and this is no coincidence. The exponent was 1/2. It came down as my coefficient, and 1/2 minus 1 is negative 1/2. So this allows us to establish, well, not this example, but we'll get now a theorem of how to deal with rational exponents. So first, before we get to pure rational numbers, we'll talk about just the derivatives for roots. So if I got y raised to the 1 over n, then the theorem says it's 1 over n x to the 1 over n minus 1. So why should that be? Well, if y is equal to x to the 1 over n, this tells me that x is equal to y to the n. And dx dy, the straightforward power rule, is n y to the n minus 1. Now, however, we know what y is. Y can be replaced with x to the 1 over n. So this is equal to n times x to the 1 over n raised to the n minus 1, right, which is n times x. So if I distribute this through, this is going to be 1 minus 1 over n. Right? So that's what dx dy is. Of course, that's not the problem I wanted. I want to know what is dy dx. Well, from the inverse rule, let me kind of put this to the side. The inverse rule, dy dx, is equal to dx dy to the negative 1. And dx dy, we just calculated, is equal to n x to the 1 minus 1 over n to the minus 1. And the reciprocal of n is 1 over n. And then when I distribute this negative through my exponent, it just flips the order of subtraction. So this is x to the 1 over n minus 1, exactly as we promised. So the next thing I want to look at is the power rule for general exponents. Let's get this done. We know what the derivative is of a root, and now we can use that fact to tell us what the derivative is for any rational exponent. So notice this is really the same form as our regular power rule, even though we've allowed r to be rational. Right? It says take the coefficient, or take the exponent, comes down, it becomes our coefficient, and you just take that exponent and subtract by 1. So let's walk through this proof. Start off, since r is a rational number, I can rewrite it as m over n, where these two numbers are integers. That means that if y equals x to the r, I could rewrite it as x to the m divided by n. Or, to make our life even easier, this is x to the 1 over n raised to the m power. Right? So that means, now I'm going to do this one slower than we have before because there's a lot going on. I've got a power here, I've got some powers there. So going slowly, the differential of y is the differential of x to the 1 over n raised to the m power. So this is just a straightforward power rule. This becomes our coefficient, and I'll subtract 1 from it. So this is equal to m times x to the 1 over n raised to the m minus 1 power times the differential of x to the 1 over n. Now this is the derivative that we just proved in the last problem, or the last theorem. So this is equal to m times x to the 1 over n, all raised to the m minus 1. And if you recall, the rule now I said, again, just like the other power rules, this comes down, the 1 over n comes down, becomes our coefficient. This exponent will come down, become our coefficient, and we subtract 1. So this differential is 1 over n x to the 1 over n minus 1 dx. And now there's a lot going on here, but I can, kind of collect all my terms, if you like, and we get that, and this 1 over m, so this is m over n times x to the m minus 1 over n times x to the 1 over n minus 1 dx. And now same base, so m minus 1 over n, I'm going to add here. So these two fractions already have the same common denominator, so it's going to be m minus 1 plus 1. So this is m over n times x to the m over n. So that's what these two fractions simplify, right? When I take m minus 1 over n and I add it to 1 over n, right? That one and that one will cancel, and all I get left behind is m over n. Okay, and then we still have this minus 1 floating around, minus 1. But recall that m over n was our r, right? So finally I can say that dy is equal, so I'm going to replace that with r, place that with r, x to the r minus 1, I forgot my dx, so I can divide by dx, and there's our result.